hang on. Wait for him to be ready. Okay, so I'm Donal Fellows, and I'm talking now about the current status of our project for compiling tcl to native code. So tclquadcode it's a native code compiler for tcl. We're currently focused working using tcl 8.6 as the source language. So we currently compile only tcl to procedures. Want to extend that, but we still haven't done yet. Unfortunately, our original plan was to make a just-in-time compiler, but it looks like at least the first version is going to be an ahead-of-time compiler, and we are using quite the most advanced technology in the room. There's a lot of cases where we are actually using stuff that is just been coming out of people's PhDs and stuff like this. So it's mostly work between Kevin, Kenny, and myself. Kevin is doing a lot of the higher level stuff, and I'm doing much more of the back-end code generation. It's 40,000 lines of heavily commented tcl, okay? And also uses Just DaCosta's LLVM tcl, which I've sort of ended up taking over as being the person doing the maintenance of that, but it's not yet finished. So that's the sort of high level big picture view. So we have a mailing list on SourceForge, which anyone who's interested is welcome to join. It's not high traffic, but it is highly technical. So and the code is in the fossil repository on core.tcl.tk. So so we're doing this because the tcl bytecode engine has basically hit a wall in terms of its performance. It's not incredibly fast. I mean, a lot faster than tcl 7 was, but it's still not incredibly fast. And unfortunately, whenever you make a change to it, it tends to make things slower, and that's not a good sign. It's also internally quite crazy because it has a lot of cases where we're doing goto in patterns that are absolutely not condoned in any form of sensible structural programming. We really want this to go faster. Now, it's possible we could make tcl go faster, maybe 50% faster by rewriting a lot of it, maybe twice to doing a new bytecode engine. But if we really wanted to go fast, we have to generate native code. There is no alternative there. And this is something which we've actually been discussing for a long time. Certainly being discussed back and forth between Kevin, Kenny, Miguel Sofa, who died last year, Don Porter, myself. I can't remember exactly who it was from Active State. It may have been Andreas Kupris, but they've certainly been involved in the discussions, even if not in the programming. And the reason why it was Kevin and myself is because we had the most spare time. And what really triggered this is a number of years ago we had some Google Summer of Code students. One of them helped produce a bytecode assembler. That's in tcl now, so if you want to actually try and write some tcl bytecode directly, you can go off and use that. It doesn't expose all tcl bytecodes, but it exposes almost all of them. And if what you do is actually unsafe, it'll throw you an error and tell you no, your bytecode's illegal. So you can't actually break tcl with that, which is the interesting feature of it. Also, Just DaCosta, when he wrote LLVM tcl, he included a demonstration that converted a small subset of tcl to native code. He made a number of really very limited assumptions. He was saying things that it's only 32-bit integers. Everything's a 32-bit integer in that example, and that's not actually true. But it was incredibly fast. I mean, the first time I ran it on some mathematical code, and it was giving. It sped it up by about 25 times, and that was the point where I thought I'd done something wrong. I mean, I actually spent a long time just validating that it was actually generating the correct answers from that, because it was just going so incredibly quick. Finally, the final thing that really spurred us to get on with it was when Carl and Bauer put up a bounty for speeding up Tcl. I mean, it kind of gave us a bit of a kick up the pants. But we're not doing it for him. We're doing it for everybody. But it's nice that there is the bounty there. It sort of encouraged us to get on. Now, our long-term aim is to support as much of Tcl as we can. Now, we ain't there yet, but we really want to be able to have it so that you can take some arbitrary Tcl code, throw it in, and sometimes it will not produce very much help because, say, if it's I/O-bound code, I mean, then what's it doing? It's spending its time waiting on the disk. You won't see much performance improvement. But if you throw in something highly mathematical, then it does an awful lot better. So the headline speedups with numeric code. Typically, you'll get up to 30 times faster. If you're working with double precision numbers, then that's typically in the region of 12 to 15 times faster. Whereas for integer code, you get that's where you get the really impressive speeds. General simple code tends to come out as being 2 to 6 times faster. If our optimizer really does a good job, it may well hit over 100 times faster. We've actually seen that in practice, but we haven't yet really been able to check how much code is actually likely to actually generate that case. And as I said, I/O-bound code, you don't see much improvement at all because that's not where the bottleneck is. String code doesn't get much faster. That's because Tcl string implementations are actually fairly good. And all the limit there is about how many copies do you do, and that tends to be whatever's driving it. So we don't actually make much difference there at all. So these are some measured speedups from a bunch of examples that are actually in our demonstration suite. So as you can see, we're getting speedups that are absolutely quite crazy. All these were done on, these timings were done just a day or two ago on my laptop. So these are pretty much as real as you can get. You can see in the impure caller case, which is, it's actually managed to actually, in that one, it's actually succeeded in throwing away an awful lot of code internally, so that it's actually managed to switch from doing an awful lot of runtime analysis of what might be going on, which is what happens when you have a Tcl obj being manipulated in Tcl. Then, in fact, it's actually managed to convert that into being able to work directly on numbers and pre-compute things. It's a truly that's the one which really impresses me every time. So these are all pretty good. So how it works. This is the standard Tcl processing pipeline. You start out with a procedure definition, which is a string, and from there it generates some bytecode that can then go into the bytecode engine for execution when the procedure is called. But what we actually do is that we then pass it through a system called Quadcode, and this is almost, in effect, it's a kind of alternate bytecode, except that this is one that allows us to do type analysis on the code. And with this, it allows us to actually, because it actually turns out that with the majority of operations, we actually do have types. I mean, these are types. So if you were to add two numbers together, you know that the result is going to be a number. And if you know that both numbers happen to be integers, then you know the result is going to be an integer. So that's an example of the kind of reasoning that we do. Now, as we proceed through things, we actually do a considerable amount of work because we actually expand the number of functions that we generate out from these things so that one procedure actually can become many different functions, each of which with a different type signature, and so so that we can actually have more optimal cases or cases where it's less optimal, but it actually does the type checks, so that you can still call it from ordinary Tcl code. So and then we've combined that with a standard library of implementations that I've written, and that then generates the actual function definitions. These can be then optimized and transformed into native code, and that then the idea is that the result is that we get code out that has exactly the same interface as the standard procedures, and that you can call in just the same way, except it is much faster. And this is it's actually working for quite a large fraction of TCL now. So that's actually, we're really very happy with it. So yes, I mean, why did we get the speed ups? Well, the big costs in TCL tend to come from memory management, type checking, value conversion. So that's things like shimmering and stuff like that. So if for example, with addition, how it actually works under the covers is that it checks if the arguments are numeric, throwing in an exception if they aren't. It converts them to actual numeric values, it then uses the actual types that it's got to actually decide exactly how is it going to do the addition. Then it's got to allocate a new TCL obj reference in order to hold the result, and then it has to deallocate the input, the arguments, and there's a lot of overhead there. So by crunching the thing with the types, we can actually throw away most of that work and leave just the additions themselves. And it turns out that this works really, really well with when we do just a little bit of work from our bytecode. Well, it's actually quite a lot of work, but it's so yeah, as I said, it's the knowledge of the operations inherent types that allows us to do much better. And we do a lot of advanced stuff to actually allow us to be able to cope with the fact that sometimes we can't actually take a decision entirely at compile time. We have to delay it until runtime, but then we do that through specialization of the procedures, type specialization. But the key types that really make a difference are that we can generate a Boolean double and int64 types directly now from tclquadcode, and those ones tend to be handled very, very well from a standard compiler. We can also do a lot of tracing of effects of decisions, and that helps an awful lot with the remaining memory management that we have to do. And it works very, very well with a good optimizer. So because we're using LLVM on the back end, that's actually, in the current versions have a very, very strong optimizer. So that's actually very, very nice. Slightly older versions, we actually cause it to have real trouble. It doesn't like just how much code we actually generate. So yes, I've mentioned splitting code paths by type. We do a lot of cross-procedure analysis, differentiation of functions by type. These are all critical to be able to actually analyze what is actually going on in ordinary TCL code and actually generate optimal code from it. Because very often you have cases whereby it's usually very good, but in some cases it isn't, theoretically. So we have to, so by doing the specialization and things like that, we can actually do a lot better. I won't show you a lot of code, because if I do that, then unfortunately it does not fit on the screen. It usually doesn't fit on, say, 30 or 40 screens. It generates vast quantities. But here's a fairly simple example that we came across recently. The version on the left-hand side is not particularly great. Let's be quite clear, but you can speed it. But by changing that to the version on the right side, first of all, this is code that becomes faster in standard TCL when you do that. But secondly, it actually doesn't just become faster, it actually becomes much more able to be optimized by our compiler. So that's doubly great. And it's actually the core of one of the examples that I showed previously. If you move that scan so that it is actually being used correctly, as opposed to being done in a fairly horrible way like that, then things are not. Then you get an intermediate version, which I couldn't fit on the screen, but that's gets more acceleration, but not as much as if you go to the version on the right. And the other thing to note is that this one is actually supporting It's supporting access to global variables. It's supporting calling standard tcl commands because for things like split and scan and binary scan, we just call out to standard tcl implementations. Life's too short to rewrite everything. So the recent work is that we can call standard tcl commands. We synthesize a call frame so that it looks just like you've been calling out of a procedure. So all the local variables that are visible from there get written out into that call frame, so that ends up with something that looks exactly like it would if you were calling just from the procedure. And this has allowed us, given us access to most of tcl. So this is actually very nice. Yes, we also have access to global and namespace variables, and this is just tremendous stuff. It's really, really useful. So the downsides of our system. Right, compilation time is very long. We have a test suite that is 145 procedures. That's taking 39 seconds or so to compile. That is a bit too long for use as a JIT. It's fine. It's not too bad for an ahead-of-time compiler, and the advantage with an ahead-of-time compiler is that that you can actually then do a lot more optimizations. Then you can run that at which means that in our case, that actually makes quite a big difference to the speed of the code. But that's quite painful. The amount of code generated is very, very large. So those 145 procedures, they get expanded, including the library, up to 578 functions, and 25 kilobytes of tcl code expands to rather a lot of megabytes of machine code. And we're worried, not so much as a disk footprint, because disk space is mostly fairly cheap, but we are worried about the memory footprint of that a bit. Not sure what we can do about it, but that's going to be work that's ongoing for a while. And as I said, yes, this most certainly does stress the downstream compiler in some cases. And with LLVM 3.9, we were having compilation times in the region of 10 minutes. And this dropped to the current about 40 seconds when we switched to LLVM 4.0. So we were very, very pleased with doing that and immediately switched over. Our coverage of tcl is incomplete. That's kind of expected. It's ongoing work. I've got a breakdown of the compilation times on the right-hand side. Prospects for improvement. The first 3 points, working through the Quadcode, I think there's a lot of room for improvement there, because that's all written in tcl, and one thing we can't do yet is compile the compiler. 4 and 5 are the parts that are in LLVM. That's already in C++, so that's going to be a lot more difficult to shrink the time on. But maybe we can switch to a different engine, because LLVM does not have a reputation for being fast, but we don't know. We haven't explored that yet. So our next steps, we've got a lot more work to do on variables. We need to, because we want to be able to support fully qualified variable names. We want to support dynamic variable names. We want to be able to support upvar, which is the one which we haven't done yet. We also want to be able to support uplevel. That's kind of useful, and we want to get an alpha release out so that as soon as we can, so that other people can actually use it, because we think once we have uplevel and upvar, we will have something that even incomplete will do a lot of good for a lot of people. So I think rather than waiting for perfection, we'll just say, well, this is not yet complete, but it could be useful for a lot of people. I think that's where we'll say that. In that case, get something out there and let everybody use it, and tell us that we write terrible code and that we should be ashamed of ourselves. So after we've done that, then we want to expand the set of types. We want to make it so that we support tcl methods and lambda terms. I have no idea how we'll actually be able to look those up. We want to be able to support being able to yield out of these things and do tail call and things like that. We would love to be able to do JIT compilation, because that would then let us integrate it into what will probably be TCL 9.0. Of course, the compiler itself needs optimization, and we want to look also for spin-off technology so that we can, so we have things in there that are actually quite useful for other people. I've got things like an implementation of closures and things like that. So it would actually be that an optimized version of it would be quite useful for other people, I think. And that's the end of my talk. So there's a lot more to go, but any questions? Yes.
So this is your thought on all the work that you're doing on Quadcode, but what's the relationship between this and NRE?
The relationship is that this code we do not generate NRE aware code at the moment. We want to fix this. That is a non-trivial transformation of the internal codes, of the internals of the code that we generate. So it's going to take quite a bit of work in order to do that, because it involves us having to actually write out the state into a structure that we can then pass around, that we can actually pass back through the NRE engine so that when it re-enters the implementation. So yeah, that's going to be fairly complicated to get that one working right. We know approximately what needs to be done, because we've done it, because I've done a lot of the work for how to make NRE enabled versions of many of the core TCL commands. But so we have a fairly good idea of how we would go about doing it. But knowing approximately how we would do it and actually getting it working in real code, big difference there. Big. Any other questions?
I'm a bit afraid of big num issue, because in TCL, when you add two numbers and it overflows the 64-bit range, it gets upcasted to big nums, and you can't know that statically.
Yeah.
So will it make the code twice as slow, because after every single operation you need to check for the overflow?
We would need to. Certainly with the implementation that we're using in LLVM, we can basically get the check for whether there was an overflow very cheaply, because there's an operation which will basically gives us an overflow flag. Then what the point is that then we would have to then say, well, in that case we will spill to a slow code path where that's all doing the big num handling. What the impact on speed this will be, I don't know. We had to stop working on the big num stuff because TCL doesn't expose quite enough of its API in order to make that work. The problem was that that the code assumed that you had a C compiler in the loop, and so it had an awful lot of hash defines involved. And unfortunately, that's the one thing we can't really process easily. We can process calls into TCL's API, but we can't actually process process those hash defines, because we are not C. We're basically a weird kind of assembler. Cross between a TCL and an assembler, actually.
I wonder to which degree certain modifications, like the assumptions that Kevin already mentioned, to which degree would these help improve things? Assumptions is one thing. Kevin, I assume they would work, but what other kinds of predictions could a programmer provide to a procedure such that I can cut this special case?
Yeah, the standard ones that are usually there are what are the input types for a function, and what are the variable aliases. Particularly, do these variables never alias? That's a very useful one.
The question is, how much sense will it make to be able to ask the programmer to provide this?
So this is the kind of thing which we're thinking about. Are people being asked to being able to provide In the case of a type assertion, it's actually relatively straightforward to see how we might actually go about expressing that in terms of tcl code, because you just say, we define a command that says that this argument, this variable must contain a value of this type, and if it doesn't, it throws an error. And that's something we can easily imagine how you would talk about that in terms of tcl code, and that's got relatively simple semantics. The non-aliasing assertion is one that we've only started discussing in the past couple of weeks, so that's early days, and we're still trying to understand exactly how much we need to do it, and how much we can instead do this by runtime actually processing, because unlike in C, we can actually definitively determine whether two variables alias at runtime. So that might mean that we'll be able to not require people to make that assertion.
Well, the decision where people might just avoid producing a copy of it for the anti.
It's as I say, this is something which it's stuff that we will have only just started exploring, and we don't know yet. There's other things where we probably will be making changes to what will actually be accepted as being tcl code at all. The big one there is being able to do traces on local variables, because we totally hate that. Because traces really do not work well with our compilation strategy. So, but again, we don't know exactly what the impact will be, and it's going to be interesting to see. The thing which I should have said, and I didn't, is that I would love to be able to take on having something like EuroTcl as a set of supported types, because they would map quite well to sort of to the sets of vector types that compilers support, and that would give a very, very nice kind of acceleration. But I have no idea what that would involve. So it's very much an interesting question to be explored.
One more question about the generated native code.
Mm-hmm.
So as it looks like now, tcl would then ship with some LLVM components, or would it just require LLVM to be available and then produce code which LLVM makes into native code?
The current situation is that if you are running the compiler, you need the LLVM parts, but once you have compiled it, you don't. So it is just if you are running the compiler. So that if you then if you took the object code, made it into the dynamic library, and then shipped that, then you wouldn't need to have LLVM there at all. We don't rely on anything in regards to that. At least I think we don't. We shouldn't do.
So you compile every possible combination of input types and...
No, we compile the combinations that are required for the code that is presented. So, for example, if for every procedure that we are given, we will compile the one that takes all its arguments as strings. Where string is actually a tcl object, and therefore could be of any tcl object type. I mean, there's no constraints there. It's just that we refer to them as being strings because they're not specialized. Then what happens is we do the type processing, and as that we decide that in this case we can actually prove that the arguments to a particular call are actually of a more constrained set of types, and in that case we'll say, well, in that case we'll generate the function that takes those arguments and then see what we actually, and then that allows more optimizations like that. So, and this is done. One of the reasons it's slow is that this is actually an iterative process. As you do more of these optimizations, you can actually enable there to be more So it's actually a very, very complex process, and we started out with using a data log-driven system to do it, but that got removed because it was way too slow.
But then the compiled code would no longer be machine independent.
No, the compiled code is absolutely dependent on the machine that which it is.
Today the compiled code.
Yeah, I mean, in principle, doing a cross compilation isn't particularly difficult, provided we have the appropriate machine description. The code we're generating is largely independent of the operating system, because we just, for all those calls, we just delegate into standard tcl commands. But there are a couple of places where it does depend, particularly for the output object format. That stuff is actually a bit experimental still. Provided you can do that, plus also describe the size of key numeric types. So that's the thing, and the size of pointers, size of words, whether it's more efficient to generate 32-bit or 64-bit integers and things like that. So provided we have all that description, then we can actually generate code for the platform. Also need to know the ID for the platform. So at the moment we're only generating for the current machine.
But at the moment you're actually producing C code and just we generate a format called an LLVM intermediate representation, which is basically a high-level machine code. And that is most certainly lower level than C. It's even low. Okay, it's lower level than C.
Yeah.
If object types are created using the tcl API, is there a future way that you can support the Quadcode compiler to handle the custom object types?
What it would most likely do by default is it would just pass them around. If that's good enough, then that's what it does by default. It's typically it makes the standard tcl assumptions that values can be converted to different types and things like that. So you have to be the usual level of careful. But apart from that, no, it should just pass them around for defining new operations. Depends on the exact type signature, but if you're introducing full new types at the Quadcode level, that is indeed quite complicated. In part because you have to define how to actually detect that these operations are present. You have to define so that you get all the type signatures actually as the input, the type analysis, and then there's all. Oh yeah. Anyway, but and then even once you've done that, then you also have to define all the stuff for doing the code issuing. So it is quite a lot of work. If you just handle it by passing it around, we do that already.
Pass mostly tokens around, hiding the objects behind there. So
that would probably just work.
We have to be careful to not lose.
But it's the same. But it's the same. It's the same. It should just be the same as it's currently in tcl, because if it's doing an invoke, it will actually calls tcl val obj. So it's doing all those things relatively straightforwardly.
Okay, so maybe we should stop the detailed discussion about